mostly focused on being available. We can deal with some inconsistencies later, even if it means like manual intervention, but we never want to be down. We want the app to be working every time, every day, every minute, and that's challenging. What you're seeing on the screen is the view of Amsterdam, the city that I live in now. From Uber's point of view, you can see like the brightness of the color represents how often an Uber car drives there. So yeah. And so our architecture, we have many servers in geographically distributed data centers, and we have a service-oriented architecture with hundreds of microservices. And it's not only about people, actually. We have, no tech talk is good enough without a picture of some kitten. So Uber is actually going into the last mile delivery business. We can deliver packages within cities. That's part of the Uber Rush service. We can deliver food very quickly within minutes as part of the Uber Eats service, and we have some like fun promotions where you can we agree with some animal shelter, and we like take some kitten from them, and people can order an Uber car with kitten, and like the money that they give them goes to the animal shelter, and then they also can keep the cat. So yeah, some fun. Right. So about open source. Our platforms are built on open source technologies everywhere. We are using Ubuntu and Debian Linux on our servers. We are using a lot of Docker. Docker was a big buzzword last year. I don't know if it still is this year, but I guess it is. And the main languages our backend services are written in are Python, Node.js, and recently Go has been gaining a lot of speed. Our storage or like further backend services include Kafka for logging, Redis for caching, Cassandra for as a key value storage basically, and Hadoop for data analytics. And the list goes on and on. We use open source technologies everywhere. But we are not only using them, we are also contributing. Every project, every service that is created at Uber is considered for open sourcing. Of course, that can happen every time. You know, there are some like business critical things that must be kept secret. Sometimes it doesn't make a lot of sense to open source something, but if we can do it, we open source things. And we have more than 80 original public GitHub repositories, also more than 40 forked repositories. And our software engineers are constantly contributing to projects in different ecosystems. I would say mostly in Node.js at this point, but like contributions from our people are, very often our people contribute. Okay, so this graph shows you how many microservices there are at Uber. This is like a historical graph. So 2 years ago, there were no microservices. Everything was served by a monolithic API service. But since then, with the number of microservices has exploded. We now have over 700 microservices running at Uber, and even keeping them running, is a challenging thing. And so I'm going to talk about 3 things that support this microservice-oriented architecture. The first is string pop, which is scalable, fault-tolerant application-level sharding. We'll see what it is in a minute. TChannel, high performance RPC, and Hyperbahn, service discovery and routing for our large-scale service-oriented architecture operations. All right. So, RingPop. RingPop is actually the project that we are developing in Amsterdam. So RingPop consists of two main things. It's a consistent hashing ring and a membership protocol. Consistent hashing allows us to consistently shard requests to the workers that actually do the business logic. So imagine you have a trip that has started. The trip has an ID, and because the trip is full of state, and you want you're doing some caching, you want the cache to be fresh, so you want that one request be routed to the one host, to the one instance, and that one instance is going to handle the whole trip. And you can imagine that the supply service, for example, or the demand service that we have, are being served on hundreds of hosts. There are hundreds of instances, and we need to route these requests consistently to one machine that is going to handle that one trip, and then it can do other things. And if, of course, we want to be available, so if that machine fails, we want this failure to be non-disruptive. We want the trip to still continue, right? If the machine crashes, we cannot afford to lose the trip. And a membership protocol gives us fault detection in a decentralized way, in a scalable way. So we will see how these two things come together. So I will dig a little deep into the underlying technology. So a hashing ring is actually like a continuous, or basically a 4-byte integer. So the first thing we need to do, we are basically placing workers on this hashing ring, or instances as we call them, and then as the requests come in, we route them to these instances based on hashing. So first thing we need to do, we need to place these instances on the hashing ring. So here we have three instances, A, B, and C, and we've run them through a hashing function that is going to just return a 4-byte integer, and that places them on the hashing ring. This determines the key space division. So every instance is responsible for the keys, for the hashing keys that are counterclockwise until the next instance. So in this case, instance B is responsible for the left half of the key space, and instances B and C have split the right part of the key space. In reality, it's a little more complicated than this. It actually never happens that this would be this imbalanced, but for the sake of simplicity, let's assume it's kind of disbalanced, but in reality it's not. Okay, and now if we want to determine which instance is responsible for a given user, for example, or a given trip, we hash the user or the trip, and it falls somewhere on the ring. In this case, users 1 and 5 have fallen onto will be handled by instance B. And the same way, user 8 is going to be handled by instance C, and user 4 is going to be handled by instance A. Now let's say instance C has caught fire, it's down. Somebody has cut the cable. And we need this thing to cause as few disruptions as possible. So our membership protocol determines that instance C is down. It removes it from the ring. And now instance A is responsible also for user 8 because C is no longer part of the ring. and but as you can see, users 1 and 5 are still being handled by instance B. So unless the instance goes down, the request is going to be routed to the same instance every time. And in the other case, if we put another instance in the ring, in this case D, it's going to take over some of A's key space, and user 4 is now being handled by instance D. So the important thing to remember again, unless something goes wrong, the request is always being handled by one instance from start to beginning, from beginning to the end. All right. And now how we do the membership protocol. So our membership protocol is based on Swim. If you've never heard of it, go read the Swim paper. It's an excellent paper. I really recommend it. It's a great read. Do it. This is we are assuming we have 3 instances, and we somehow want to keep the membership, and we want to keep it in a decentralized, scalable way, and Swim allows us to do this. So in the steady state, these instances cycle through their membership list and randomly, in given intervals, ping their neighbors. And if nothing happens, they just happily ping, and everything is fine, you know. But if instance B goes down and instance A decides, tries to ping it, it doesn't get a response back. But we don't know, you know, like sometimes packets get lost on the network. It might be just a temporary thing, you know. We don't want to jump to conclusion that instance B is down. So we want to be sure. So what happens is that instance A asks another instance, in this case instance C, to do what is called an indirect ping. It sends a ping request to instance C, and instance C pings instance B on A's behalf. And so this is for the case where, you know, like a link between A and B has been broken, but still the link between C and B is fine, so we don't want to mark B as faulty because it's still there. Just A cannot reach B, but that's not a big problem. So the indirect ping fails, and now A declares B as suspect. That means it's not yet declared faulty. You know, it could be just a temporary failure. We don't want to be causing many disruptions unless it's really necessary. So it's just been declared suspect. But after some time, I forgot something. What's important here is that this protocol is based on what we call gossiping. That is, in these pings, we gossip, or like we piggyback, what we call it, information about the membership to other instances. So the next time A pings C, the ping carries the information that B has been declared suspect. And so in the next ping, the information that B is declared suspect goes to instance C, and after a little while, you know, when B doesn't respond back, it's actually declared faulty. The best thing about this approach is that it's very scalable. It's doing what we call infection style dissemination. It doesn't. It goes randomly. It randomly disseminates information about membership, but this random infection style dissemination eventually gets to all the nodes. But the beautiful thing about this is that the traffic is constant per node. So that when we grow the cluster, nodes don't need to keep connections to every other node there is. They are just pinging some subset like in constant intervals. So it's very scalable, and we have clusters with 1,000 instances in production. We have tested it to 2,500 instances, and we just don't have enough hardware at this point to go further. But we think it's going to be fine up to 10,000 instances of this running. So that's something about the scale of Uber. Like we have a service that has 1,000 instances in production. Okay, so how does Ringpop actually? How does one use Ringpop? So Ringpop is an application level middleware. Requests come into the service. Ringpop, based on the hashing ring and the membership, decides whether it should handle the request or forward it to some other instance. And so you can imagine something like this. This is just pseudocode. Don't look too closely at it. So if you look at the diagram in the bottom, these are our three instances. A request for user 1 comes to instance A. Instance A is not the owner of the user based on the consistent hashing. So it forwards it to, but it knows where it should go immediately. So it forwards it to instance C, and instance C handles it and replies through instance A and sends the response. So this is what the code could look like for some kind of business logic on users. So you have seen that there's a lot of RPC happening. Many services, many pings happening, many requests and responses flying around, and we used to use HTTP, but there were many issues with it. HTTP is a complex protocol. It's kind of slow performing in some cases. So we came up with our there was a need to make something more reliable, faster, and so we created TChannel. TChannel was created with the service-oriented architecture in mind from the start. So you are not calling hosts; you are calling services. We wanted to be able to trace any request in our service-oriented architecture, so that we can do diagnostics, we can do performance testing, and tracing of the requests. We want it to be easy to implement in the languages that we use. Also, we wanted it to support multiplexing. That is, you can have one connection open and send many requests. You don't have to wait for the response as you would need with HTTP. With HTTP, you can work around it by using multiple connections, but then you're using more connections, and it's not as scalable. We wanted it to support arbitrary serialization. We still use a lot of JSON, but the problem with JSON is that it's slow to parse and produce. We have found that many of our services were basically doing one thing all day, and that is like parsing and producing JSON. So we actually started using Thrift, which is a different serialization approach. And we wanted, of course, it to support high-performance forwarding, because that's what we do a lot, as you have seen. So TChannel is a binary protocol, and it's binary because we know there are fixed points in the TChannel header that we can access directly without needing of any difficult or complicated parsing. And based on these headers in fixed positions in the byte stream, we can determine the forwarding. We don't need to parse the whole request in any way. So that allows the very fast forwarding. And yeah, there's a request ID which actually allows us to do the tracing I described. We can just trace any request by its ID throughout the whole network. Yeah, so again, TChannel is open source. We have 4 implementations in Node.js, Python, Go, and Java. And we've also built tools to support it. tcurl does, it's just curl for TChannel. And tcap allows us to trace and diagnose TChannel requests as they fly through the network. Yeah. And of course, if you have a large service-oriented architecture operation, you need some way to do service discovery and routing on this large scale. So that it's one thing to have one service that is like nicely working and it's reliable and it uses consistent hashing and everything is working fine, but you need a way to communicate between these services. So that's where Hyperbahn comes in. Hyperbahn gives us service discovery, request forwarding. Clients have to do almost zero configuration. You just need to give it one Hyperbahn instance and it will bootstrap automatically. IP address of one Hyperbahn instance and it will bootstrap automatically. And also, Hyperbahn allows us to do circuit breaking. That means if one service is misbehaving, it doesn't respond, we can cut traffic to it so that it doesn't disrupt services that are downstream to it or upstream. And also allows us to do rate limiting. If, again, one service is misbehaving, is producing many requests, we want to limit it dynamically so that, again, it doesn't disrupt more of our architecture. So Hyperbahn is actually based on ringpop. The Hyperbahn routers form a ring, and services connect to this ring. Services do not connect to every node in the Hyperbahn ring. They just have a subset of them, which we call an affinity group. So you can imagine service, when the service starts, it contacts one of the Hyperbahn nodes, and the Hyperbahn node tells it where it should connect, where its affinity group is, and it connects there, and then it's ready to respond to requests. So this is what a request flow could look like in Hyperbahn. So service A connects to Hyperbahn. And basically service A wants to do a request to service B. Yeah, that's the goal. So service A sends the request to Hyperbahn. Hyperbahn this determines where service B's affinity group is, forwards the request to one of the routers in the B's affinity group, and then forwards it to service B. Service B again determines where it should actually handle the request, forwards it to the correct instance, and then the whole thing goes back. So you can see there's a lot of routing happening, and and forwarding happening, and that's only thanks to TChannel that we can do this in a high performance way. So conclusion. Uber is both open source user and contributor. We have a large service-oriented architecture based on our open source projects. You can, there's good documentation. You can really go to GitHub, take a look, play with it. These projects are Ringpop, TChannel, and Hyperbahn. There's plenty more there, and we still have a lot of interesting challenges ahead. We've been around for like 4 or 5 years, something like that. Our architecture is still evolving, and yeah, so things will change, things will break, but a lot of interesting stuff is happening. So, thank you. Yeah, Uber is hiring if you want to work on this and more cool stuff. Get in touch with me. Also, if you want to take an Uber, you still don't have an account, you can use a promo code Marek for you to get 250 crowns off your first ride. Yeah, so that's all from me. I'm ready to answer any questions you may have. All right. Yeah, I think you were first.
I have 2 very quick questions.
Yeah.
One, do you have any Paxos or Raft implementations, also particularly if you're open source? And secondly, I imagine you must collect a lot of data running Uber. So what are you doing with this data? Are you selling it, or? I bet you it's worth millions, if not more, the data. So
Yeah. Okay. Yeah. The first question was, do we use some kind of Raft or Paxos implementation? Answer is, kinda. Like we use Cassandra and we used React, which are both based on these things, but we don't have anything in-house based on these two. So, kinda. And the second question was, we collect a lot of data. What are we doing with the data? Are we selling it or not? So we are definitely not selling the data. Yeah, we have a big Hadoop operation. We are analyzing a lot of data, but we are definitely not selling the data. No.
what are you doing with it?
So you can imagine that, okay, I'm not sure I can actually talk about it a lot. But
It's all friendly, so it's okay.
Yeah. Yeah, there's a lot of space for optimization in routing, for example, of the cars, and yeah. That's about everything I can probably say here. Yeah, I'm sorry. Yeah. I think, yeah. Here.
When you say user as a key to the hash,
Yeah.
which attributes do you mean? Is that I assume that's not a username. Is that an IP address or?
Yeah. So we work with UUIDs throughout. Yeah, sure. The question was, how do we determine the identity of the user, basically? Yeah, so we don't use usernames. Every user is associated with UUID, so we use these UUIDs as the source for the hashing. Right. Yeah?
Can you talk about security, encryption,
Yeah. The question was about security and encryption with TChannel. This is all happening internally. We don't do any encryption on the application layer. I believe there are IPsec things happening, in the lower layers of the network, but yeah, you wouldn't use TChannel to connect from your cell phone to our infrastructure. We still use HTTP and REST-based approach to get to the end device. Yeah.
So is that each node stays
Yeah.
And if it dies, another node take over.
Yeah.
What happens in the background? You probably have to replicate the data, so you use Cassandra for it, or it's stateless, or it's some stateful and replicate data as they come.
Yeah. So the question was, what happens if if the node actually dies in the middle of the trip? How do we like load the state? So there's a couple of things we do. One, we use Redis for caching. So you would stay the transient state in Redis as one place, or we have a couple of storage services based on Cassandra, based on React, where we store the data so that it can be loaded in case the node dies.
Okay, so basically, when the data comes, it's immediately stored.
Yeah. Yes. So the advantage there is that like your caches are fresh, and also there are other services which only store really transient data that get refreshed every couple of seconds. So if the node, if one of the instances dies, the data gets refreshed from the source very quickly. So like we get like a 4-second or something like that disruption, but it's like not a big deal. Yeah.
Does your protocols or tools guarantee that the packet, once it's sent, it gets to the actual endpoint that was required? You have like you said, you have like 800 microservices, right?
Yeah.
So I really don't believe that any request would actually go through all of them. But I assume that handling a request requires you to handle like, let's say 50 of your microservices. So is there any way you guarantee that this package is not being lost in the middle?
Well, so the question was, is there any guarantee that the requests get where they are supposed to go? The answer is no. Like you can always lose the packets somewhere in the network, but what you can do is you can do speculative execution. That is, you actually ask 2 instances for some request, and you use the first response that comes in, so that if one of the packets is some lost somewhere, you still get the second one. You can also wait for the responses, and if it doesn't come in, you repeat it. But then, of course, you are faced with some latency issues. Yeah. So there are ways to work around this, but of course, if a packet is lost somewhere in the cable, it just gets stuck in the cable. No. Yeah, you need.
Do some echoing.
Yeah.
So and returns.
Yeah. So thanks to the fact that we have request IDs, we know that we send a request with an ID, and we are waiting for a response with an ID. So if the response doesn't come in, we can safely resend the request, because the destination service knows that it already served it, so it can send the same response again. So we can guarantee that it's going to handle the request only once, and as well we can guarantee that the source service is going to handle the response only once, thanks to the IDs. Yeah.
Can you elaborate more on how you deal with recoveries? For example, if customer's mobile device loses connection and then recover, or you lose connection between your data set.
So yeah. Well, what used to happen is that devices would basically ping our data center every couple of seconds, and they would get the whole state of the application back, and it will just display the state. But we are kind of moving away from this approach. So the mobile application knows what data it should request, and it just asks our backend services for the data. And if the connection gets broken, your application won't update for a couple of seconds. But when the connection comes back, it will just load the data that is necessary.
How do you deal with conflicts?
Well, I don't think there's a big room for conflicts, really. The application is fairly simple, actually. So you just, when you make a request to get a car, you just commit with pressing the button. The request either gets to the server or it doesn't. And if it gets there, it gets processed on the server, and you will never you wouldn't send the request twice. So there's I don't think there's a lot of room for conflicts, actually. Yep.
I just briefly checked the source code of Hyperbahn or GitHub.
Yeah.
Written in Node.js. And my question is, why decide to write it in Node.js instead of, for example, Go or Java? And second question is, have you had a tough times making it stable? Because on the internet there is a lot of complaints about Node.js even not being dispatched, being dispatched twice, etc.
Yeah, so the first question is, Hyperbahn is written in Node.js. Why didn't we choose Go? Basically, Node.js at that time was the language to write things in. At Uber, there were software engineers able to write things in Node.js, so that's the basic reason. And the second question, did we have problems with Node.js? Yes. So yes, we've had problems. That's why actually Go is gaining a lot of speed at Uber now.
Are you considering rewriting it to something else, or it just mature, stable, robust enough for you?
We are considering all options.
So unfortunately, we are really out of time. So thanks, Marek, for the great talk.
Já si vezmu tu prezentaci. Bylo to super. Počkej. Momentálně tu. Já to vypnu asi. Tak, ty video. To bylo lidí, že?
To tak dlouho jsem zastupoval samodary.
Odpadlík.
Proč jste psali Hyperbahn? Proč jste z toho nepoužili nějaký zvuky, nebo něco takového jako service registr?
You speak English, right? Yeah. So I will repeat the question in English. No.
Sorry.
So the question was, why did we write Hyperbahn? Why didn't we use some out of the box